see how it works. The goal of all of this is to be able to start this unit with a single button push. So we need a method to connect and disconnect our idler motor to both source and output current. We need a method to get our idler motor to spin up to speed before we connect the source current. And we need to capacitor balance our idler motor so that the generated leg has the same voltage as the supplied legs. I've made the decision that before I put all the balancing capacitors in place, that I might as well go ahead and put the unit into its final form factor, which is to say its final safe form factor. Playing with these kind of voltages, these kind of amps, there's only a certain point at which having things strung out across the floor remains a good idea. I'm pretty sure I've passed that point. So a little tour here. Power will come in here at the top and feed into these line 1, 2, and 3. This will be the master contactor that will throw anytime the motor is energized. So this center line will be the one that the start capacitor is attached to. So master contactor on with the start capacitor on. That will send the unbalanced phases, the out of time phases, down the line. The motor will start. The 1 second timer will kick in. It will pull the start capacitor out of the circuit and simultaneously energize the output contactor. This contactor receives the voltage from the motor leads, and then when it's energized, passes it on through to the wires that will exit the case here. So power in at the top, into the motor, from the motor into the secondary contactor, and on out. That's the basics of it. Now we have to do is put all the pieces in place to make the logic of it work. A bit of a guided tour of where we're at. So I've begun mounting parts into the case. So beginning at the beginning, I'll go through the power and start sequence. 240 single phase comes in via these two leads, and live neutral comes in here. The live neutral is necessary because I need 120 volts to feed this transformer. The transformer provides DC to feed the solid state relay. Oh, and we also need 110 for the contactor coils. So initial plug-in, nothing happens. But here is the master switch, currently a temporary master switch. When you activate the switch, it closes the circuit and allows this 120 volts to feed into the transformer. The transformer energizes this 24 volt contactor, and it energizes the solid state relay through the timer switch. So both these come on at the same time. It's important that the solid state relay be among the first things that comes on to make sure that the starting capacitor is ready to go before we actually attempt to start the motor. So when the contactor is energized, it, number one, passes the neutral over to the coil of the main contactor. Now the hot side of the coil is tied in with the master switch. So the hot side became live as soon as I threw the switch. But the neutral side did not come live until the transformer woke up, came online, fed the 24 volts into the contactor. That makes sure that the solid state relay and that the timer switch are ready to go before we actually send any juice down to the motor. So as soon as this relay closes, it closes the neutral side of the coil, which will initiate the contactor. The contactor closes, sends voltage to the motor. The starting capacitor is linked across from one of the hot feeds into the third leg of the motor. The motor will begin spinning immediately on getting the voltage because this starting capacitor is in circuit with it. Simultaneously sends voltage by means of here to the timer switch. So on about a half-second timer, this timer switch kicks out, which cuts out the feed to the solid state relay. So then the starting capacitor now comes offline, and now the motor will spin fully up just using these two live coils. At the same time that the timer switch removes the solid state relay from the circuit, it energizes the final contactor into the circuit. So the downstream power feed, which is leading off to the machinery that this rotary phase converter will be powering, this contactor does not come online until the starting capacitor is out of the cycle and the motor has spun up. So I'm going to plug it in and confirm that it all works the way I think. So I've hooked up this temporary power whip. It's hooked up to an 60 amp service, which is actually a little bit on the shy side for this. But assuming it's all wired correctly, I think it ought to go ahead and start the motor. The motor draws 29 amps at no load, and of course can surge to double or triple that on startup. So let's see how it works. Throwing this switch is gonna route power, half the leg of power to this contactor, and then it's gonna route full power to that transformer, which is gonna initiate the sequence. And there it is. So, with that taken care of, now that I can reliably start it and shut it down, next thing is to go ahead and apply the balancing capacitors. I've done a lot of reading about safety with these, as far as having the contactors set up in such a way that on power failure that the unit does not come back on. The only way I can see that that's even possible is if you do the push button start, where one switch turns the unit on and then you push a momentary switch in order to actually start the unit up. I want the unit to just start with a single throw of a switch. If the power goes out while you're running your rotary phase converter and you forget all about it and walk away, then when the power comes back on, the rotary phase converter is going to turn back on. I don't really see that being a problem. If you are running a lathe or a mill in the middle of a power outage, you need to at least have enough common sense to reach up and turn off the lathe or the mill. And if you don't turn off your rotary phase converter, that's not a big deal. It'll start back up when the power comes back on. It'll just provide a power feed to your lathe and your mill again. I don't see that being a big safety issue, so that's the way I'm going to leave this thing set up. One more startup just for the fun of it. Hooray! So we're about to begin the capacitor balancing process. The goal of the capacitor balancing is that the generated voltage on the third leg tends to be underneath the voltage that are supplied. So these two outside legs, A and B, these are supplied from the wall. So they get the benefit, if you will, that they have current coming from the wall, and they get the current that's due to the inertia of the motor as it's being used as a generator. This leg gets nothing from the wall. It is strictly a generated leg from the inertia of the generator. So in order to balance the capacitor out to produce consistent voltage across all three legs while it's under load, we will add capacitors across the supplied legs into the generated leg, so that when it's time for the generated leg, that it kind of has a little bit of an extra kick. So to do that, in the instructions I'm following, we're going to add capacitance at the CP point between A and C until the voltage of AB, which is the supplied wall voltage, is approximately equal to the voltage of B and C. So in the beginning, the voltage across B and C is going to be in the very low 200s. I'm guessing it's going to take, I don't know, something north of 200 microfarads to bring this up to approximately the same voltage as the wall voltage. But we'll just go in steps and we will mark down our progress with each step. Okay, so step 1 is complete. Step 2, we're going to increase the capacitance across B and C until the voltage of AC is about 1.08 times the voltage of AB, which is to say until the voltage between A and C is 1.08 the feed line voltage. This is clearly too much capacitance across CS because the voltage at BC is just too high. What I'll do next is I will try it again and I will back off capacitor P and see if that brings the voltage at BC back to a reasonable level. So when I reduce capacitor P back to 200 with capacitor S at 100, I get a resulting voltage of 255 across AC, 252 at BC, and 243 across AB. So I'm also going to try running the BC capacitance at 150 because I want to get the voltage from BC to be very similar to the voltage from AC. And they're currently 255 to 252, which is close, but I'd love to see them get even closer, so let's see how this does. Alright, so that's my final position. At 150 across B and C, my voltage is 255, 259 for the two generated legs versus 243 in from the wall, which is approximately 1.08. My amperage coming in, I'm 3.8 amps on this leg and I'm 4.2 amps on this leg. So those are close to each other, which is great. So that is the basic capacitor balance. And lastly, following the instructions again, we will add what will be a small amount of capacitance across the AB lines, across the incoming supply line. And there is a point of adding capacitance that will actually reduce the line current while the system is at idle, and there is a point that will increase the line current while the system's at idle. So what we want to do is find the point that it is reduced as much as possible. So we're going to begin with 50 microfarads, which I suspect is too much, and then we will reduce it in increments until we get it as low as it can be. So without any, we're drawing 4.2 amps across L1. So we're going to add in 50 and see if that increases or decreases the current across L1. No surprise that that actually took the current up a little bit. So now we're going to try an 18 microfarad. All these capacitors are rated at 370 volts or higher. If I were to put in a capacitor rated less than 370 volts, it could be disastrous. Which is to say the capacitor could explode. Explode's a hard word. It wouldn't destroy the house, but it would make a mess. Here we go. 18 microfarad. In that configuration, the amperage went down. 3.46 in line 2, 3.71 in line 1. Okay, here we are catching up after a little bit of work's been accomplished. Not a terribly exciting thing to watch happen, so just kind of an update. These 4 capacitors are the AC capacitor bank. The jumper from them comes from here down to A and C. These 3 capacitors are for the BC bank, so they jumper over here into B and C. And finally, these capacitors are the much smaller capacitors for the AB portion, and they simply jumper from A up here and B down here. No reason to tie them all the way back into here when we can just pick up those. And I cleaned up and installed this pigtail. So this is a 4-prong connector. It's listed as a 30 amp 250 volt connector. We're running a smidgen more than 30 amps through it, at least on startup. But this is strictly for testing. These conductors are not big enough. In use, this unit will need a number 4 conductor. In fact, it's going to need a number 4 conductor. I'm going to need to pull these out and replace them. These are number 6, and number 6 is not going to do the job. It's plenty for this motor, but since we're going to be drawing power downstream, then these need to be swapped out with a number 4 conductor. So it needs a number 4 conductor in, and then it needs number 4 conductors internally, so that we get number 4 all the way through. So there have been no major changes. It is as it was when it was tested and balanced, just cleaned up and mounted, and ready next to install the control panel. The control panel will consist of this start and stop mushroom button, and I have 3 The control panel will consist of this start and stop mushroom button, pull to start, push to stop. And then I have 240 volt voltage indicator. So my plan is to have the start stop button and then the green light voltage indicator, which will obviously indicate and in fact read out to you the voltage, so that you can at a glance have some degree of confidence that the voltage output is within spec. And the way to do that is simply to compare this leg to one of these legs, which is to say all I need is a 240 volt indicator that when there is 240 volts between BC or A to C, either one, it really doesn't matter, then the light will light up and indicate to the user that the system is online. And those I'm going to mount, I've given it some thought, and I think I'm just going to mount them right here on top of the unit. The start-stop button will simply be like right here, and voltage indicator next to it. If the user wants to have remote control of the unit, all they have to do is run 2 conductors that close these 2 terminals, this terminal and that terminal. It's a 120 volt circuit. Close that 120 volt circuit and the unit starts up. So I think that will be convenient for if anyone cares to have the power switch remote. This power switch can stay where it is, and you can simply tie it into another switch somewhere remote and start and stop it from either place. Alright, so I went ahead and took a Sawzall and cut off the shaft for safety. Just you don't want that big shaft sticking out there to catch things, to wind things out. So right here, it's just this little button. It's nice and smooth. I went ahead and filed it while it was running, which smoothed it out substantially. And then a last look inside the box before I close it up. Here is the wiring to the mushroom button power switch. There is the power on voltage indicator. It's 2 leads. They're 300 volt rated, but obviously they don't need to carry a lot of current. And they come down into the A and C port, which obviously enough reads you the voltage across A and C, which is another way of saying the generated voltage of the C leg. In general terms, this number should be something like, at no load, it should be 250, perhaps 255, because with no load on it, it is a little bit higher than once it's under load. So here it is. Simple. Starts out, what do we got? 253 on that generated leg. Our amperage across here is nearly identical, about 3.65. This is 355, that's 365, and it seems to be running smooth and in balance. Final thing, we can't really say we have a rotary phase converter until we have rotated some phases and made some machinery work. So, I have an output cable there, not a very big one, but we're only running a 3-horse motor. It leads over here, temporary connection, leads over there. I'll join this in a second. That pigtail leads off to power the lathe and the mill. So let's fire up the rotary phase converter and see if the lathe and mill work. It's alive. Alright, that seems to be working. And 238 under load, which is just right. So I'm calling it good. This rotary phase converter is built. And hey, thanks for watching.